All right, so welcome to today's class in Mathematics 1. Let's get started. First, as often, a quick organizational remark. Tomorrow's class, so tomorrow, 21st of November, the Tuesday class will not take place in this room. Instead, we will be in room 2300 once again. That's the room that we've already been last time we had to move. So for tomorrow, please don't come here. Please instead come to the room 2300. All right, let's start with today's topics. So this week, we are talking about game theory a little. In particular, we'll apply some of the things that we've learned about matrices, about equation systems, about vectors, to a specific topic that might be very useful in other contexts. And we'll learn about one little branch of matrix games, or of game theory, and that will be matrix games in particular. So let's first set the stage. And this is this first part here, where we'll learn about bimatrix games. This is the more general aspect. I will focus on a more specific part of that in the following chapters. So here's a very prominent example of these bimatrix games that's called Prisoner's Dilemma. And you find this turns up very often in practice, and in many, many economic examples you'll encounter this Prisoner's Dilemma. So let's talk about this for a few minutes first. The setup is the following. A crime has been committed. There's two suspects that have been caught by the police, and they are now interrogated separately. Each of those two has two options. They can either confess or they can deny any involvement in the crime. The outcome of that whole thing depends on what both individuals choose to do. Basically, there is three possible options. Both could confess. In that case, they would get a lighter sentence, and they would both be sentenced to 3 years in prison. Both could also choose to deny any involvement in the crime. In that case, the police doesn't have quite enough proof to warrant a sentence for 3 years, but there is some amount of proof for some aspects of that crime, so they will still be sentenced, but they will only get 1 year each. And then there's a third option, and that is one could confess and the other one could deny. And in that case, the one that confesses will walk free, and the one that denies any involvement for his stubbornness will get a severe sentence of, let's just say, 7 years. And the question is, of course, what should they do? Let's assume for a moment they can't communicate, and all the information that we have is encoded in this game here, right? So in particular, they don't have to fear any repercussions afterwards for whatever choice they make. And of course, that is a very severe assumption. So what is the optimal strategy? What should those criminals do? As I said, we assume, not only here, but in all of the following, that we have complete information. So that means all aspects that are relevant, all possible actions, all possible payoffs are known to each of the participants. And they're all encoded in this payoff information of the game, so how many years they will get. This is known to all parties involved, and all parties know about this. So each of the criminals knows that the other one knows that the other one knows, and so on. Also, no cooperation is possible. So in other words, you can't change the game. Each party chooses one of the available strategies completely independently of what the other does. They can't talk to each other. And they can't decide to change the rules. Yeah, those are set. And finally, we assume perfect rationality. So that means all parties behave completely rational, and their sole objective is maximizing their individual gain. They don't care about the rest of the world. All right, so as long as we have these assumptions here, well, what should those criminals do? Now let's maybe quickly summarize the options that I have. So we have two parties. They each have two choices. They could either confess or they could deny. And we said, if both confess, they will both get 3 years. Right? So in this case, let's say 3 years and 3 years. So let's say we have, this here is the criminal 1, and this here is a criminal 2. And what I write here applies for the criminal 1, what I write here applies for the criminal 2, right? So they both get 3 years. In this case, if they both deny, they both get 1 year, so that's also easy. We have a 1-1 here. Now, if one denies and one confesses, right, what happens here is the one that denies the crime will even get 7 years. So in this case, criminal 1 denies, criminal 2 confesses. So here, criminal 1 will get 7 years, criminal 2 will walk free, so 0 years. And in this case here, it's just the other way around. So here, the first criminal confesses, so he walks free, and the second one denies, so he'll even get 7 years. All right, so based on that information, what should those two do? Well, if you look at the possibilities from the point of view of criminal 1 for a moment. Let's say criminal 2 will confess, right? That means we're somewhere here in the set of possible outcomes. If criminal 1 assumes that, then what is the best strategy for him? Well, he could either confess and get 3 years, or he could deny and get 7 years. Yeah, so what's the better outcome? Of course, he will confess. If he knew that criminal 1 also confesses. Let's say we assume criminal 2 denies. What should criminal 1 then do? Again, there's two possibilities. He could deny or he could confess. What's the better outcome? Well, he would confess, because that would save him 1 year in prison. So in both cases, no matter what the other person does, the best choice for criminal 1 will be to confess. And now we can do the same analysis from the point of view of criminal 2. So again, criminal 2 has two options, confess or deny. And let's say criminal 1 will confess. What will criminal 2 then do? Well, if he confesses, he gets 3 years. Oh, sorry, other way around. If he confesses, he gets 3 years. This is the 3 for criminal 2. If he denies, he gets 7 years. So in that case, criminal 2 would also choose to confess. And of course, in case criminal 1 chooses to deny, again, there's two options for criminal 2. He could either confess and get 0 years, or he could deny and get 1 year. So again, the better option is to confess. So what he'll do is also, he'll choose to confess. And that means the outcome of this game will be this situation. He will both get 3 years. Right? And what we've just seen here is the case where each of those two criminals, each of those two players, has what is called a dominant strategy. So no matter what the other person does, it's always better to confess. Right? So even if they could talk to each other, it would still be better to confess, no matter what the other person does. Right? Let's say they agree on denying, it would still be better to betray this and confess. So they will land in this situation, even though this situation here would have been much better for both, even individually, right? So it's not just the sum of punishment that is less than in this blue situation, but for each of them, they would get 3 years here and only 1 year here. It would have been much better to achieve this outcome, but that won't happen, given the assumptions of this problem, of course, right? I already said one assumption is that all the information is encoded in the game, so there is no revenge that to be feared. Even if one of the criminals confesses and the other denies, it's not like he could walk away and then be killed by some other party of the mafia. Of course, if we include this information, the whole setup might not work anymore. So there's nothing to fear from confessing in that case, apart from the possible prison time to be spent. Right? And that's why this is called prisoner's dilemma, because for both parties involved, this is where they will land, and this would have been a better outcome for everybody. Not just for the society as a whole, so to say, for both prisoners combined, but for each individual prisoner. That would have been better, but they won't get there. And that's where this dilemma comes from. And of course, there's multiple applications of similar setups. Many of them have to do with some kind of a free rider problematic. Think, for example, of climate change, right? If each one of you has a chance to invest in doing something against climate change, for example, you buy an electric car instead of a petrol-fueled car, that would be an investment you have to make. If each one does that, then as a society, we would be better off, right? We might get away with 1 or maybe 2 degrees of global warming, and that might be a lot better than everybody continuing to pollute, and we might end up in a very catastrophic event that will at least cost us a lot of money. We all know this, but still, if you as an individual had to make the choice, problem is, if you invest in battling against climate change and all the rest doesn't, the outcome will still be catastrophic and you've lost your money. So in that case, it would be better for you to not do anything. Let's say all the others choose to do something about climate change. Everybody but you buys an electric car. Then your impact is very small, so the catastrophe will hopefully be averted, but you didn't have to invest. So again, you're better off. And this is also some kind of a prisoner's dilemma, obviously, right? For everyone, as an individual, the rational choice would be to do nothing. Don't spend any money. But as a whole, the society as a whole, of course, it would be much better if everybody took the necessary steps and hopefully get to a better future outcome that every individual would then profit from. Right? It's not that you as an individual would be able to somehow escape this catastrophe. You'd also incur the massive costs once this thing hits. But still, it's better for you to not invest. And of course, the only way to get around this is to change the rules of the game in some way, right? So we need to change the payoff. We need to change the rules. It's not like the market will regulate this in any way if you just let it play by these set of rules. So again, you have some kind of prisoner's dilemma here, and that applies to almost every kind of setup where somebody can ride for free, and maybe basically society has to pay for that. All right, so that's this setup of prisoner's dilemma. That's, as I said, one of the prime examples for these kind of games. And as you can see, basically the information that you need is what strategies are available to the 2 players. Right, here's 2 players, this one and this one. In this case, they both have the same set of strategies, but of course that might be different. And then what payoff will they get from any combination of strategies? And that payoff might be different for the 2 players again. So here we have one entry for each of the players for each combination of strategies. And that's why a setup like this is called a bimatrix game. because for each of the players, you basically have a matrix that encodes his or her payoffs. And as there are 2 players, you need 2 matrices to describe all possible payoff situations. And you just encode the strategies as the rows and the columns of this game, of this matrix. And that's why you usually refer to those 2 players as the row player and the column player. Right? The row player chooses one of the strategies encoded in the rows. The column player chooses one of the strategies encoded in the columns. So that's the formal definition here. Right? Formally, this is a 2-player finite strategic or non-cooperative game, or we usually use the term bimatrix game. To specify that, you need the number of strategies for all parties involved. So you have a number of strategies for row and a number of strategies for column, M and N. And you need 2 payoff matrices, and we'll usually denote those as a R for the row player and a C for the column player. And then the number of rows and the number of columns is called the set of actions that are available to the row and the column player respectively. And those 2 matrices are called the payoff matrices. Right? And as I said, their entries encode what payoff row or column get for any specific outcome of the game. Now formally, if we have a bimatrix game like this, we define 2 sets as R and SC. And those will be the so-called strategy sets for row and for column. A strategy basically means deciding how to play. And the usual simplest setup here is to use what we call a pure strategy, and that means just to select one of the strategies. Right? For the row player, it means selecting one of the rows. So in this setup, either confess or deny. And for the column player, it means selecting one of the columns. So again, confess or deny. And of course, if we have a matrix, we can easily encode this in a vector that just assigns a 1 to the strategy that we choose and a 0 to each strategy we don't choose. Right? So in this setup, for example, choosing the strategy confess for the column player means column's strategy would be 1, 0. Right? You just take the ordering of the columns. So confess is the first column that gets a 1 and all the others get a 0. Right? And the same can be done for the row player, of course. And that would encode the set of so-called pure strategies. And now there's one extra twist. And you'll notice I haven't written the set of 0, 1, so I haven't done it like this here. But instead, I put down the interval here. And what does that mean? Well, what we do here is we also have the option of just assigning probabilities to each of the actions. So the number between 0 and 1 can be interpreted as a probability of choosing this action. And then, of course, if we want this interpretation to work, all probabilities have to sum up to 100%, so to 1. That's the second requirement here. Right? And that means instead of selecting one of the pure strategies, it could also be a good idea to randomize. Maybe not in this setup, but in other setups it might be a good idea. So you could decide something like, I'm going to flip a coin. Heads, confess, tails, deny. That's my strategy. Right? So that would mean you're playing a strategy of selecting each of those 2 with a probability of 50%, 1 over 2. Or you could say, I'm going to roll a dice. Let's not flip a coin, let's roll a dice instead. And let's say if I get 6, I'll confess, and for everything else, I'll deny. Right? That would mean your chances of confessing are 1/6, and your chances of denial are 5/6. So that would be your strategy in this case. Probability of 1/6 for confessing, and probability 5/6 for denying. And it just means you don't fix a strategy ahead, but you assign probabilities. And then, when you have to make a choice, you make some kind of experiment to determine which of these strategies will actually be selected. You could also interpret this in several ways. Of course, one interpretation of this probabilities approach might be if you repeat the play. Right? Then in each of the repetitions, you again have the choice of taking one strategy or the other. And in the long term, you'll choose all of those strategies with a certain probability. Right? So in this case, if you do 100 repetitions of this, then the column player will choose confess in about 1/6 of those 100 repetitions and deny in 5/6 of those repetitions. Right? Whereas the column player here will choose, will choose confess in 50% and deny in 50% of the situations, so 50-50. Another possibility of interpreting this is not by doing repeated plays with the same actors, but instead imagine you have a whole population of players and the game takes place in very many places at the same time. Right? So there's more than just one police station and more than just one pair of criminals in this world. Let's say they all get caught, and each of those makes a decision to confess or deny. And let's say this probability distribution here that just represents the probability in the population. So on average, half of the column players will choose to confess and half of them will choose to deny, for example. So this is a way to interpret these probabilities if you want. Question? The result, I'll get to that in a moment. Let me just finish the formal definition first. All right, so that's why formally we say a strategy is again a vector assigning one number to each row or one number to each column, and the number has to be between 0 and 1, and all those have to sum up to 1, so we can interpret them as probabilities of choosing that specific strategy. All right, so this is sometimes referred to as a mixed strategy, and assigning a 1 to one action and a 0 to all the others is referred to as a pure strategy. So now if we have a pair of strategies, so the column player selects a strategy, and again this is a vector from SC, and the row player selects a strategy, again a vector from SR. The question is, how can we compute the payoff? So what is the outcome of that game? And remember, we have those two payoff matrices. So of course, if we have pure strategies, we can just identify the entry in the matrix and take that as the payoff. If we have mixed strategies, what we can do is we can compute the expected payoff. So the average payoff over a large population of games being played at the same time with this probability distribution. And if you want to do this, this is the way to compute that. Right? We take in this case, the payoff matrix of the row player, and we multiply it in this way. I'll show you an example of that in just a second. And the same, of course, works for the column player. The selection mechanism is basically the same. It's just the payoff matrix. This is, of course, different here. All right, so here's again prisoner's dilemma. In this case, I've used negative entries because that's a punishment, right? And a payoff somehow suggests it's something good. So I want a negative payoff because it's something bad. But again, same information, right? If both confess, each get 3 years, so each has a payoff of -3. If both deny, both get -1, so 1 year in prison. And if one confesses, then the one who confesses gets 0 and the other gets -7, and here's the other way around. So those are the two payoff matrices for prisoner's dilemma, and basically that's the same thing as I wrote down here, just split into two matrices. Right, and now what we have, possibly, we could choose a pure strategy. So for example, the role player might choose this pure strategy. What does that mean? That means he's assigning a probability of 1 to the first row and a probability of 0 to the second row. So in other words, the role player chooses to play row 1. On the other hand, this strategy here would mean assign a probability of 0 to the first row and a probability of 1 to the second row. So in other words, the role player would choose to play row 2. And of course, the same can be said about the column player. And here's an example for a mixed strategy, right? In this case, each of the possible actions will be selected with the probability of 1/2. So in other words, both criminals toss a coin and then decide based on the outcome what they're doing. Right? So probability of 1/2 for the first row, probability of 1/2 for the second row. Now let's take a look at the payoff. So let's say row chooses to confess, row goes here. Column chooses to deny. Deny is this strategy here, second strategy. So when we're interested in computing the payoff of this situation for the row player, so we're using the row payoff matrix here. Now what happens here, let's first take a look at this part of this matrix vector multiplication. What happens here is this weight of 0, when you do the multiplication, that will be assigned to all entries in the first column, and the weight of 1 will be assigned to all entries in the second column. Right? So that's the expected payoff, given that the column player plays this strategy here, for each of the possible strategies that row has. If we do the computations, this here is the outcome. Right, so now you can see if row chooses, so given that the column player chooses this strategy, if row chooses to play row 1, then the outcome will be 0. If row chooses to play row 2, the outcome will be -1. And in our case, we already fixed that up ahead. We said that row chooses to play confess, so 1/0 is the strategy. And that means if you do this matrix multiplication, the outcome is 0. So that's the payoff for the row player in this situation. And of course that was expected, right? What we said is the column player chooses to deny and the row player chooses to confess. So we'll end up in this situation and the outcome is 0 here. So basically, multiplying a matrix with a unit vector amounts to selecting a part of the entries of the matrix if you want. Yeah, so the vector that comes to the right of the matrix is responsible for the columns. So here you select the second column, right? This one. That's the outcome of that multiplication. The vector to the left selects rows. So this selects the first row, right? This entry here. And of course, it doesn't really matter if you do this multiplication first or this multiplication first, the outcome will always be the same. Right, so that's for the column, sorry, for the row player, and of course you can do the same thing for the column player. So here's the same expression, but now with a C, the column payoff matrix. And again, we just do this matrix vector multiplication, we get -7 as the outcome, and again, that's what we expected. Okay, and of course you can also do this with mixed probability, with mixed strategies, sorry. So let's say, as we just had in our example, let's say the row player chooses to play this strategy, 1/6, 5/6, so confessing with a probability of 1/6 and denying with a probability of 5/6. And let's say we want to compute the outcome of the column player for this. So we use AC. And let's say our column player chooses 50-50. So this is the strategy the column player chooses. Then what will the outcome be? Let's do the rate multiplication first. So we just copy the first vector. And then what we do here is we multiply the first column with a weight of 1/2 and the second column with a weight of 1/2 and add those up. So for each row, we get the expected payoff for the row player if he chooses that row, given that the column player already has made his choice in that way. Just give me a second to complete that. All right, so if we do the computations, we get minus 3/2 here, and minus 7/2 minus 1/2, that's minus 8/2 here. Right? And now again, this is the expected payoff for the column player if row chooses the first row. And this is the expected payoff for the column player, because we started with AC here, right? If row chooses this strategy, pure strategy. Now row in fact decides to mix. So he has this mixed strategy. So well, the outcome in the end is going to be 1/6 times minus 3/2 plus 5/6 times minus 8/2. Right, so we get, let's see, what do we get? Minus 1/4. And, well, what is this? This is minus 4, minus 2, so this is minus 10/3, is that right? Hopefully. I'll let you complete the computations yourself. So again, that's the payoff for column, right? Because we started with the column payoff matrix here. For row, we could of course do the same computations, but we'd have to use the row payoff matrix in this place. And again, that's just the payoff for this specific pair of strategies, right? So we pre-selected those, and now we want to know what the payoff would be. We didn't optimize anything at this point. So I think you were first. When you have two pairs of matrices? Yeah. So the question is, when I have two payoff matrices, how do I deal with that in this situation? And the answer is that depends on what I want to know. I have one payoff matrix for the row player and one for the column player. And then the question is, do I want to know the payoff for the row player? And then I use the row payoff matrix. Or do I want to know the one for the column player? And then I use the column payoff matrix. And of course, if I want to optimize in a certain way, and we'll come to that example, then I have to deal with both independently, right? The row player optimizes and the column player optimizes. And of course, whatever one of those players does is always influenced by the choices of the other player. But each of the players, again, they can't talk to each other, right? They can't discuss what pair of strategies they want to choose. Each has to make a decision based on this information for himself or herself. So that means, let's say I'm the column player, I'll have to take into account what the row player might do if I choose this strategy and whether this would still be a good choice. And the point is, I have to select a strategy that is best under all possible selections of the row player for me, right? Or I'd have to somehow find out what the row player is going to do. Maybe that would also be possible. Maybe there is a strategy that I know row will always play because it's always an advantage for him. And then I can optimize my strategy based on that information. Yeah, again, both players have complete information, and both players know that the other knows and that the other also behaves rationally in the same way. Right, you were next. Did I use AR instead of AC? Really? Sorry about that. Let's see. So AC has a -7. Yeah, that's right. I used AR. Sorry about that. So just replace column by row and vice versa in everything I said. All right, any other questions at this point? Yes. Mm-hmm. Mm-hmm. We'll see examples of that. So the question is, what if a player is indifferent between possible strategy choices, and we'll see examples of that later on. Yeah. So again, perfect rationality, so that means he or she will really be indifferent. It doesn't matter to him. Yeah. Why are we transposing what? The row strategy? We're transposing that because of the rules of matrix multiplication. So you mean this one here, right? So basically my point is, if you want to do this matrix multiplication, right, here you have a 2 by 2 matrix. So that means you have to, if you multiply something from the right, that has to be a 2 by something, right? In this case, a 2 by 1. If you multiply from the left, you'd have to match the number of rows, right? So that has to be a something by 2. And that means we need a row, right? Not a column, but a row to be formally correct for this matrix multiplication. That's why we're transposing this. All right, so let's go on. Let's discuss Nash equilibria, and then we'll take a look at the first homework, I guess. So the question that we've been asking is, what can I say about the outcome of the game, and what can I say about the choice of strategies? Well, as a player, of course, I want to know what is my best possible strategy. What should I select? And I will also want to know, what will my opponent do? And of course, there is perfect information, so I should be able to analyze that all, and I should be able to make a prediction on what my opponent does, what is best for him or her. And then I will also know what the outcome of the game is. Yeah, so I should be able to know my payoff up front. And one important concept in the analysis of games is the concept of Nash equilibrium. The basic idea here is a Nash equilibrium is a situation, that means a choice of strategies, where none of the players will gain anything by changing the strategy unilaterally. Yeah? Given that the other player stays at this point, the strategy selection is fixed, can I gain anything by doing something, by choosing another strategy, by doing something different? If the answer is no for both players, that's called a Nash equilibrium. Yeah, because if I am at this point, for whatever reason, none of the players has an incentive to do something different. One example, prisoner's dilemma. Yeah, you remember those were the payoff matrices here. Maybe let's go back to the notes here. So those were the payoff matrices for prisoner's dilemma. And we argued that both players will choose confess and will end up in this situation. So is this also a Nash equilibrium? Well, the question is, if just one of the players would change his strategy, would that give him an advantage? If the answer is no for both players, then we have a Nash equilibrium. In this case, if criminal 1 would change his strategy, right? He currently gets 3 years in prison. If he change, that means this would be the new situation, because the column strategy is fixed, and he would get 7 years in prison. So that is definitely not an advantage. There's no incentive for the row player to change anything. And the same is true for the column player. Currently gets 3 years in prison. If the column player changes, he will get 7 years in prison. So again, there's no incentive for column to change anything about this situation. So this is a Nash equilibrium. What about this point here? Well, if we're here, then the row player gets 1 year in prison. If row changes, we move to this point and he will get 0 years. So definitely the row player has an advantage to change. And that means this cannot be a Nash equilibrium. All right? So if you want, the Nash equilibrium is kind of a stable situation. None of the players involved have an incentive to use another strategy as long as the other player doesn't change anything. And there may be more than one of these equilibria in a game. Here, this is one Nash equilibrium. There may be more than that. And again, we see examples of that. Formally, let's skip over all this. Let's get to the definition right away. Let's say we have a bimatrix game specified by 2 payoff matrices for row and for column. And let's say column fixes a strategy. So X star is column's strategy. And that is from the set SC. Again, remember SC was a set of all possible column strategies, including the mixed strategies. Then we'll say a row strategy is called the best response to X star if it maximizes the outcome for row, basically, yeah? So row says, well, if I know that column chooses X star, what is the best move I can make? That's my best response. And formally, that means the payoff for the row player is, for this specific strategy, for the best response strategy, is at least as large as the payoff for any other strategy. There might be other strategies that get the same payoff, and those would then also be best responses, but there's none that gets a better payoff. And of course, the same can be defined from the point of view of a column player. So let's say row fixes a strategy, Y star. Then we just have to use the column payoff matrix here. And the definition of best response to Y star for the column player would be a strategy that maximizes his payoff compared to all other choices he has. Again, always under the assumption that row strategy is already chosen to Y star. Okay, so that's called the best response to some strategy of the other player. And formally, a Nash equilibrium is simply a set of 2 strategies, one for row, one for column, that are best responses to each other. So X star is the best response to Y star, and Y star is the best response to X star. And that means none of the players has an incentive to switch to some different strategy. It will not gain anything because that is already a best response to what the other player does. Right? Formally, of course, you can again write this down as inequalities here. And then a special case of that is the Nash equilibrium in pure strategies. Well, that simply means you have an equilibrium where both X star and Y star are pure strategies, so just 0, 1 vectors. All right, we just discussed prisoner's dilemma, and we found that this here is a Nash equilibrium, and it's even an equilibrium in pure strategies. And then there's this celebrated theorem by John Nash. It's not as easy to prove as it looks, so we're not going over the proof. In fact, that was one of the reasons he was awarded the Nobel Prize for that. So he has shown that for a bimatrix game, there always exists a Nash equilibrium in mixed strategies. Maybe not in pure strategies, but if you allow for mixed strategies, you always get at least one Nash equilibrium. Okay, so in a way, these equilibria are the points of the game where we will end up in the end. And there might be more than one possible choice for that. But before we discuss more theory, I guess it's time to take a look at an example. And one possible example is this homework problem that you hopefully all took the time to at least give a try. So this is the game Battle of the Sexes, and let me maybe go through this in some detail, because it might help to clarify some of the questions that you have been asking yourselves. All right, so this is a scenario that obviously takes place before the time of instant or any reasonable communication. The two parties involved can't speak to each other. There's two parties, Romeo the role player and Celia the column player, and both hope to spend the evening together. In their small local town, there's just two venues where they can go. They can either go to the stadium and watch a baseball match, or they can go to the bar and attend a concert there. Their prime concern is to be together for the evening, so none of them wants to spend the evening alone, but each of them has a specific preference on where to go. Romeo would rather go to the baseball game, and Celia would rather go to the concert. So here's their payoff matrices. The one for Romeo, you can see here, that has two zero entries, and the zero payoff will be received if Romeo and Celia end up spending the evening apart. And that's also the case for Celia. So if one chooses baseball and the other chooses concert, none of them gets any payoff. If they end up together at whatever venue, each of them gets a positive payoff, and that's at least 2 in this model here. So if they both end up at the concert, Romeo gets a payoff of 2. Celia even gets a payoff of 3, because in addition to being with Romeo, they also end up at the concert, and that is what Celia prefers. And for Romeo, the situation is reversed. So if they both end up at the baseball game, Romeo gets a payoff of 3, because that is his preferred place to be, and he gets to spend the evening with Celia, and Celia gets a payoff of 2. All right, so that is the setup here of this Battle of the Sexes game. Any questions so far? Right, so classic bi-matrix game. And we jump right to part C here, because I haven't defined zero-sum game yet. So let's discuss the question, does this game have Nash equilibria in pure strategies? Well, does it? Maybe let's take a look at what you have found out. Let's take a look at tweetback. Just give me a second to give you the link to that. And there's a question on here, does Battle of the Sexes have Nash equilibria in pure strategies? And possible answers include no, there are no pure strategies Nash equilibria, or there is exactly one, or there are even more than one. And I'll just write down the payoff matrices here briefly while you make your decision. All right, give you 20 more seconds to cast your vote. All right, so let's take a look at the outcome. And most of you said there is even more than one Nash equilibrium in this case, and those who voted for that are correct. So let's take a quick look at how this works. Let me pull up the sheet once again. All right, so let's say you want to find the Nash equilibrium in this setup. So here's the payoff matrices for Romeo and for Celia. I want to know if there is any Nash equilibria in pure strategies, right? So we can always assume the players choose one of the rows or columns, so there is no mixing, no probabilities involved. So let's first say Romeo chooses to go to the baseball game. So that means he chooses this row here. Maybe I should color that. So Romeo chooses baseball. That means he chooses this row of his payoff matrix. And of course, he also chooses this row of Celia's payoff matrix. Now, what about Celia? Let's look at this payoff matrix here. So if Romeo chooses row 1, what is Celia's best response? Well, she would maximize her payoff by also going to the baseball game, right? Otherwise, she'd get 0 payoff, here she'd get 2. So if she knew that Romeo was going to the baseball, she would, of course, also go to the baseball game. So let's assume Romeo chooses strategy 1, 0, meaning he go to the baseball game. Then what is Celia's best response? Well, that is also the strategy go to the baseball game, also 1-0. In this case, Romeo gets a payoff of 3 and Celia gets a payoff of 2. So if she chooses that strategy, that means we are in this situation, and of course the same is true here. Now, is this a Nash equilibrium? Well, for Celia, obviously, she has no incentive to change to this strategy because that's her best response, right? The question is it also Romeo's best response? So given that Celia plays this, would Romeo have an incentive to change to that strategy? Well, he currently gets a payoff of 3. Changing would mean he gets 0. So obviously there's no incentive for him to switch, right? And that means Romeo's best response to this strategy is also the one that we started with. So then, Romeo's best response to that is then 0, 1, and that is the strategy we have chosen initially. And that means this pair of strategies here is a Nash equilibrium. Each of the strategies is the best response to the other. Or in other words, given that we are at this point, none of the players has an incentive to change. Right? And notice there is no way that Celia can get to this point because she can only change her strategy, the column strategy. And all of this is under the assumptions that Romeo has fixed this first row already. So if she changes, she'll only get here and never here. Right? That could only be something that Romeo could do. Okay, so this is a Nash equilibrium. Now let's take a look at the other possible situations. Again, let me write down the two matrices. So now let's say Romeo would choose strategy 2 instead of 1. So he go for this row, right? So we've now analyzed the situation where Romeo chooses row 1. Let's see what about if Romeo chooses row 2. So now assume R chooses, well, the strategy is then 0, 1. Well, that also means he chooses this row here in Celia's payoff matrix. What is Celia's best response to this? Well, if we know we are in this row, then the best possible outcome is this entry here. So Celia will select this column. And of course, this selection also applies for Romeo here. Yeah, so this is Celia's best response. Celia's best response is then also to choose 0, 1. And let's look again at Romeo. Right? If we know that Celia is choosing this column here, then what is Romeo's best response? Well, will he choose row 2 or row 1? Obviously he'll choose row 2 because he gets 2 here, and row 1 would only earn him 0. Right, so Celia's best response is 0, 1, to which Romeo's best response is again 0, 1. And again, that means this pair of strategies are best responses to each other. So that's a Nash equilibrium. Okay, so in this game we have 2 Nash equilibria in pure strategies. One is here, both go to the baseball game. One is here, both go to the concert. And of course, in practice, that is not something that is desirable because now no one knows what to do. Right? If there was only one Nash equilibrium, it would be clear that it's the best choice for everyone involved. So that's what we'd end up with. Now we could end up with both, and it would still be a stable situation for both players involved. All right, any questions so far? Yes. Mm-hmm. Mm-hmm. So if you do the computations as I did in the videos, the whole point of those is to provide you with one possible solution. So you'll end up with one Nash equilibrium, but you might not get the others. If there's more than one, you might not get those this way. You'd have to do a more involved analysis to get those. Usually we will only be interested in getting one, because in a certain way, for the matrix game setup that we'll discuss later on, they will all be the same. Yeah, so that will not be a concern later on. Just for this example, I wanted to point out that there may be more than one Nash equilibrium, and this may of course be the case later, but for that setup that we'll discuss later, the payoff will always be the same for all equilibria, so it doesn't matter which one we choose. Okay, this is different here in this bimatrix setup. Yeah. So if you did what? This first row here? Let's give it a try. So you're saying we have a R equals 3002, and you say a C is 0203, like this. So if this was the game, well, let's see, we can analyze that. Let's say we first consider, let me actually paint this. We will first consider row 1 again. Let's say Romeo chooses row 1. What is Celia's best response? Well, her best response would be, again, to obtain this 2 here. So we're in this situation. And then Romeo's best response to this would be to change to row number 2. So in this case, there's no Nash equilibrium where Romeo chooses row 1, right? That doesn't work. So let's have a look at row number 2. If Romeo chooses row number 2, then what is Celia's best response? Well, her best response will be this, because she gets a payoff of 3 here, and she only gets 0 here. So that means we'll end up in this situation. Is that an equilibrium? Well, for Romeo here, there's no incentive to change to row number 1 now, because that would mean he gets 0 instead of 2. So this here constitutes a Nash equilibrium, right? None of the two players have an incentive to choose a different strategy, but we've lost the other one by this little change, right? So in this case, we only have one Nash equilibrium pure strategies. All right. Good. Maybe if there's no more questions about this one, let's take a look at part D of the problem statement here. Show that the strategy pair where each player chooses their preferred event with probability 3/5 constitutes a Nash equilibrium in mixed strategies. So what I'm saying here is there's even a third Nash equilibrium now in mixed strategies, and it looks like this. And I want you to prove that. Well, how do we prove that? Well, let's take a look at that. First, let's fix the strategies here. So Romeo is our row player, so he plays the Y strategy. He chooses his preferred event with a probability of 3/5. Romeo prefers baseball, so that's strategy number 1. So he chooses this strategy, 3/5, and then we have 2/5 left for the second entry. Right? So with a probability of 60%, Romeo will go to the baseball game, and with a probability of 40%, he'll go to the concert. For Celia is a column player, and we usually denote the column strategy by X, just a convention. She'll also choose her preferred event with probability 3/5. Her preferred event is going to the concert. That's the second strategy. Right, so she'll choose this, and then 2/5 for the baseball game. Okay, what we need to prove is that each of those strategies is the best response to the other. So let's maybe first take a look at Romeo's point of view. Say we know that Celia chooses this strategy. And now we want to find out what is Romeo's best response to that. So assume we know Celia plays X equals 2/5, 3/5. What is Romeo's best response? Well, to know that, we'll have to compute Romeo's payoff. So let's say Romeo plays strategy Y1, Y2. And we want to find out what the best values for Y1 and Y2 are. Then let's compute the payoff for Romeo. Well, there will then be Y1, Y2 times Romeo's payoff matrix. Romeo's payoff matrix is this here, 3, 0, 0, 2, times, and we know Celia's strategy already. Celia plays 2/5 and 3/5. So that's the payoff. And we can just do the computations here. Let's see, it's y1, y2 times 2 over 5 times 3, that would be 6 over 5 here, and 6 over 5 here. And what do we find out? We find out that the payoff in the end is 6 over 5 times y1 plus y2. And y1 plus y2 is 1 because that's a probability distribution. Right? So they need to sum up to 100% to 1. So we get 6 over 5. What does that mean? Well, that means that the payoff for Romeo is completely independent of what Romeo does in expectance. Right? So no matter what response he chooses, Celia has already fixed the expected payoff completely. What does that tell us about choosing strategies for Romeo? Well, that means it doesn't matter. Every possible strategy that he could choose is a best response because they all have the same payoff, 6 over 5. There's no better option for him. So that means every strategy that Romeo could choose is the best response for him to this strategy of Celia, which was 2 over 5, 3 over 5. In particular, the strategy that we started with, so this one here, this would also be a best response, right? So from your Romeo's viewpoint, this all works out nicely. From Celia's point of view, of course, things are mostly the same. So let's do this once again, just for practice. If we look at Celia, the claim is almost the same. The claim is, well, if I knew that Romeo is playing this, what is my best response? So Celia would assume Romeo plays 3 over 5, 2 over 5. Find Celia's best response. And she do the same analysis, but now with her payoff. So Celia's payoff. So now we have to use Celia's payoff matrix, and Romeo is again the row player, so he'll play 3 over 5 and 2 over 5 times Celia's payoff, which is 2003, times, and now let's say Celia chooses any strategy, x1, x2, and we want to find out the best values of x1, x2. Well, if we do that, what do we get? 3 over 5, 2 over 5 here. So this first multiplication here is that gets 2x1 and 3x2. And that means we'll end up with, let's see, 6 over 5x1 plus 6 over 5x2. So this is 6 over 5 x1 plus x2. And again, same as before, those sum up to 1. So the payoff is always 6 over 5. Yeah. Again, that means if Romeo chooses to play this strategy, the payoff is always 6 over 5, no matter what strategy Celia chooses. And again, this is about the expected payoff, right? We don't have a concrete realization of that situation. This is about a probability distribution that Romeo chooses. So again, as before, every possible response is best. It doesn't matter. In particular, the one that we started with is the best response. So every possible strategy for Celia. Here's the best response. 2, 3/5, 2/5. Well, and in particular, that means this pair of strategies. Let's start with a role player, maybe 3/5, 2/5 for row, and 2/5, 3/5 for column is then a Nash equilibrium. All right, so that might be one situation. This whole thing can be resolved. Both of them can just randomize with each specific valuation involved here. So Romeo randomizes with this probability distribution, Celia randomizes with this probability distribution, and at least they get an expected payoff of 6/5. So they maximize their chances of getting a good payoff in the long run. If they repeat this game every evening, in the long run, they'll end up with a payoff of 6/5. All right. Questions about this one? Yes. So the question is, if I wouldn't have given you the pair of strategies, how would I come up with that? That's actually not an easy question, and I'm not going to answer it in full generality, but we are going to look into that for the specific case of zero-sum games. I guess I'll defer that discussion to tomorrow if that's okay with you, because there's a lot to say about that. The short answer is linear programming. I hope you are familiar with that. Great. We'll apply that tomorrow then. Any other questions? And maybe let me just complete this 6-1. There's one question that we haven't discussed yet, and that is B. Is Battle of the Sexes a zero-sum game? I haven't discussed zero-sum game yet, but I will. But just to put it short, for a zero-sum game, basically that means the two payoff matrices are very closely related. More specifically, what one player obtains, the other player loses. Right? So whatever one player gets, the other player will lose. That is a zero-sum game. So the question is Battle of the Sexes a zero-sum game? And here's a quick tweetback quiz about that. You should have thought about that, hopefully. And also, now that we've discussed most of 6-1, I'd like to ask you for a quick feedback on how difficult you found this problem here. All right, I'll give you 30 more seconds. Okay, let's take a look at the difficulty rating first. Not very surprisingly, most of you are leaning towards the hard maybe medium, but very few will find that easy. I mean, that is to be expected, I guess. That's your first encounter with mathematical game theory, probably. It does take some getting used to this way of thinking. Yeah, I'm aware of that. Again, we'll discuss an easier situation tomorrow, and that is a situation of zero-sum games where the analysis becomes a whole lot easier. But we mostly use the same ideas. So let's take a look at the second question. Is this actually a zero-sum game, Battle of the Sexes? And the answer is it's not a zero-sum game. So most of you are right. Again, in a zero-sum game, what one player gets, the other loses. And if you look at the payoff matrices here, that was a change. So those are the original payoff matrices, I think. Yeah. So for example, in this situation, Romeo would get 3. If that was a zero-sum game, that means Celia would have to lose 3. That is not the case. She gains 2, right? So obviously this is not a zero-sum game. Zero-sum basically means you play for money and the winning player gets something from the losing player and vice versa. That's the classic play for money situation between 2 players. Okay, whereas in non-zero-sum games, both players may gain something at the same time or both may lose something at the same time. That was the case in Prisoner's Dilemma, if you remember that. Usually both players lost something because they had to spend some time in jail. Again, that was not a zero-sum game. And that's where the dilemma comes from. And for those zero-sum games, as I just said, the analysis will be a whole lot easier. And we'll talk about that in more detail and with a lot more examples tomorrow. So I think that's a good point to stop for today. Again, tomorrow we meet in 2300. Please don't forget that.